Hi my friends, let me show you something very interesting now. This is the Mississippi River and this is the St. Louis town in United States. You see something extraordinary. This is an arch called the St. Louis Gateway Arch, which is tall of about 200 meters or 630 feet. This is a special construction called Catenary. This is a catenary curve. Today we study this interesting special curve, which is not a parabola. The idea from which it started in such constructions comes from a chain hung at 2 points, as you can see in this demonstration. You recognize the catenary curve at the Golden Gate Bridge in San Francisco. If you flip it over, you get the St. Louis Gateway Arch. Concrete constructions resist compression and not tension. This is the assembly we create and animate today. It consists in 20 pieces like this one, which are considered to be hanged in these 2 points as in the previous video. We start with a little mathematical theory. This is the formula for catenary curve. We use Inventor, standard millimeters IPT, sketch in XY plane, and instead of a line we use an equation curve. You see here how it looks. We don't use a parametric equation but an explicit equation. I prepared some values now to transpose that equation, this one. Y is b multiplied by hyperbolic cosinus of x divided by a. B and a are 2 values I'll explain you. 20 multiplied by hyperbolic cosinus, open parenthesis, 1 radian. This is the unit, multiplied by x and divided by also 20 parentheses. We place here 2 values, minimum and maximum, 70 and 70. Here is minus 70. It looks nice, yes, but where is the graphic? I press home and we see the graphic. Okay, this is the catenary curve for that values. But we use other values. I prepared here a new sketch for you to be visible. Here you see the distance between the two hanging points are 120, 100. To start with these values, we change the equation. Edit, right click, and edit equation curve. Take care of the new values. 19.273 is this, and 24 is the other. The x minimum is minus 70, x maximum is 50 to make 120. Okay. Now we can measure dimensions. This is really 120 and this must be 100. Yes, but with a small difference. Important is that we can control this kind of curve. I place here dimension visibility to be hidden, and we have something like this. Yes? Good. However, our goal is to create the assembly, right? Standard millimeter IM. Place. The unique object is this one. Place grounded at origin, because we'll connect this with the other. Firstly, let me change the position in order to obtain the presentation of Inventor 2024, not 2014. 10 years ago I made this. Good. Now we have the first link, and we add other 20. Let's place the next one. Place, link, open. Constrain, insert. This goes here. Apply. This is grounded, you see, but this is mobile. I don't like to have this grounded. I eliminate the grounded, and we know that here is the center point. I make it visible right here. Also this axis is there, and I make it visible. I constrain the axis of this with the axis of here. Apply. And I also place the center point of this circle over the center point of the assembly. Okay, now I can rotate this first link. Good. I hide that visible work planes and work centers, and now we have a very nice combination of the first two links. I continue by adding the other 18 links. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. You see in the browser that we have 20 links. We use the insert for all of them. This comes here. Apply. Next comes to the next. Apply. And we continue with all the other. Now we can move anything here, as you can see. Yes, but the location is chaotic. We have to respect these two dimensions. This is from a plane down and from a vertical plane to the right. Let's do this. We develop the object origin from the browser and we make visible this plane. Now I apply constraint of 120 between this plane and this point. Apply. The same with the other plane, but the distance is 100. This plane was selected and now I place the other but with minus. Okay. visibility. Now you see this point is fixed. Yes? I cannot move this. I can only rotate. Okay, now we must apply dynamic simulation to see what happens. We activate the dynamic simulation, environments, dynamic simulation, and you see a lot of revolution joints. I close this. A lot of mobile groups. I collapse them because all I want is to apply gravity. Gravity, I don't have a vertical line here, so I copy the gravity acceleration, copy, and use vector components, paste. You see the direction is not good, but I use minus to be good. Now is okay. I apply, click here, and let's see what happens. You can see what happens. Remember that there is no any friction, so it moves to the infinite. 10 seconds, and you see the continuation because only 1 second was memorized. I think that this doesn't ends ever, so we have to apply some frictions between the links. I go back, not construction, and click here to eliminate the arrow. We can measure the diameter of the hole, M, from Monaco to this circle, 4 millimeters. We need this dimension. And I open this standard joints, double click, 1 degree of freedom, rotation. I select edit joint torque, enable joint torque, coefficient of friction. I put here a high value of the friction coefficient, and the radius is 2 millimeters if the diameter is 4. Okay, the first link was solved. Now let's go to the other. Double click, TOF, enable joint torque 0.2 and 2. Okay, and I go on to the other. And these were the last links to be modified, adding the friction coefficient. Then I launched the run, which took a long time, almost 13 minutes. After almost 13 minutes, when Inventor computed all the movements, I can run for you in 10 seconds all this movement. You see, with that great friction coefficient, we have this time of moving. Yes. I want you to see also that I placed here all that frictions torque to have this situation. Once again, I run for you. I didn't take collisions into account, and you have to accept that, because it would have taken me too long. Okay. Since we have the formula for the St. Louis Gateway which is here in feet, let's try to create this curve. Start standard millimeters IPT, sketch XY, and we use equation curve as explicit. I write here the formula: minus 630 multiplied by hyperbolic cosinus of 1 radian multiplied with x slash 239.2 plus 1,260 feet. The limits are minus 315 and 315 feet, half of 630, yes? But we don't see anything here. Oh, we see. Take a look here. Okay, this is the arch from St. Louis, my friends. Now comes an interesting topic. What I present here is based on the existence of the components that appear in the assembly. Regarding this modeling, you have two options. One, to contemplate what I do and apply my actions by creating your own components of this assembly. And two, try to create the assembly using the actual components you see in the tutorial. If you want to create this assembly independently, you must own the component. That is, they must be yours. As separate creations that I made for the purpose of showing practical aspects in the tutorial, you can download the components only from assets. Access to assets is done by subscribing minimum to the level Journeyman membership. You see here the levels of membership: Core, Journeyman, Patron, Professional. Excepting Core, the other ones include the previous ones. That's all for today. Thanks for watching. Bye bye.